All right, so John mentioned that we're going to give you a little overview intro to start with, and the intent of this is to get you to understand what the bats are doing, how sound behaves in the environment, and how the bats use it. Because ultimately, yeah, we want to know what bats are out there. We also want to know what they're doing. And this turns out to be a very complex operation, trying to sometimes tell one species from another from these signals, as we'll see, because they're not really accommodating us to make always signals that are different from one species to another. And so being able to understand what they're doing to put these things into context helps us a lot to be able to know when we can and when we can't make decisions on saying who this bat is and what they're doing. But also understanding the fundamentals of what's going on gives you much greater ability to be able to interpret new situations. We're not just going to give you a cookbook guideline of steps to do this, but give you a fundamental, hopefully give you, leave out of here with a fundamental understanding of all the moving parts of this whole operation in here. And so Echo101 is what we call it, and it's going to be about the biology and some of the physical understanding of sound. And getting into the physics of sound is very important because from the get-go, we need to understand that the sounds that we're going out recording and interpreting behave very different than our intuitive understanding of sound. And I'll explain how and why that is, but it creates a process in which we have to intellectually interpret what the sound is doing because it does not behave like we expect it to do at the higher frequencies that bats are using. This is an older picture, and I'll start off here just to show that this is like legacy work that goes way back in that we've got the bat there bare on a person, and this is all, anytime you see these, this is indicating old stuff because this is pre-white nose and where we don't have the decontamination and separation protocols and so on. So just from the get-go, let's all understand and appreciate that working with bats, whether capture or any other thing, is a difficult endeavor because bats are perhaps one of the most difficult taxa to survey and monitor because they're operating up in the dark where we can't see. They're in the sky where we don't go. They often roost in places that we can't fit in and look at them. And for the most part, they make sounds that we can't hear. So it's like this invisible taxa of bat, even though like 1 out of every 4 or 5 mammals on the planet is a bat. Most places you go and you ask people are there bats around, they'll tell you no, they've never seen a bat because that's the difficulty in it. So our tool that we often use have for a long time is to go out and catch the bats and see what they're doing. But of course, there's a lot of limitations on this because the bats are operating up in the full 3-dimensional sphere realm of the sky and don't often come down, many species, to where we put our nets closer to the ground. But when we catch them, we can get these up close personal experiences with the bats, and we can assess things like sex and gender and reproductive status and so on that we can't or won't be able to do from our sound recordings. But yeah, we can get these nice up-close personal things, and the bats are very nice taxa to work with actually, because when you catch them, handle them gently. In short order, they will just stay around with us, and very often we have these images like this because you hold out the bat, you're ready to go, we're done processing it, it's like, you can go now, and they're just gonna sit there and hold on. So we used to just like put them up on our shoulder or something, and sometimes they climb up on your head and they just like hang out for a while before they feel like they're ready to go. But it's kind of nice because you feel like they're not like totally frightened of you. But there was a time before white nose when I was getting enough of these, I thought maybe I'll get a full collection of these. I can do a calendar of bats in matching hair colors. And of course, we all know they go in the hair and get tangled. So, this is the camouflage. So that's a big brown bat. This is a red bat. And of course, hoary bat. You can see get there. But on to what we're here for. So for most of history, we humans did not understand how bats get around in the dark. And although we have some species like this that have exaggerated parts in their body that sort of give a clue as to what sensory system might be in use here. And here's another one in the UK, similar morphology. In fact, it was 1790, Lazzaro Spallanzani interpreted that the ears were involved, actually. And he did some simple experiments of having bats fly around in a room, and then darkened room, and then he put wax in their ears and noted they can no longer negotiate the room. And he did not make that leap to that there was sound that humans could not hear. This is a big part of the Enlightenment and understanding and advance of science, is that there were things beyond human corporeal senses in the universe. But Spallanzani wasn't yet there. He thought somehow the bats were using their ears to see visually. And of course, when he included the ears, they couldn't accomplish that. But so it wasn't really until 1939 with Don Griffin, who with a simple microphone sensitive to higher frequencies and vacuum tube amplifiers and so on, that he was able to document that bats were actively making sounds, and then did a series of elegant experiments to support his hypothesis that they were using the echoes to be able to get some form of imaging in the darkened room. And so, of course, we all know this now, that bats will go out and echolocate. We teach this in grade school, that they're making sounds and they're going out. And we think of this as one of those like amazing things that animals can do that humans can't. And in fact, you all could teach yourself to echolocate. You could train yourself to do it. You could start making sounds, and simple enough. You just like put a book in front of your face and close your eyes and make sounds about. You'd be able to know, or if I'm holding the book, you'd be able to tell me when the book is in front of your face or not. You're using your ears and perception to do that. And there are some who promote that that's an important life-saving skill to learn, because you could learn to echolocate crudely enough to be able to like exit a building that's burning, smoke-filled building where you can't use a light even to see your way. You can find the doorway, the stairway, and so on. Humans can do this, and a lot of humans have gotten pretty good at that. But as we'll see, bats can still do much better than you would ever be capable of doing that. But what does it do for the bats? So what it does for the bats is bats are very vulnerable when they're roosting. Many of them, of course, go into torpor, and so when they do that, so they're very defenseless. And their forelimbs, of course, are modified into wings, so they don't have nice claws and such. So they need to go to places where it's out of reach of predators, and with echolocation, they can penetrate into dark spaces, but a lot of them just do that by getting into tight little crevices where predators can't get to them. But the bigger part of this is that it opens up this enormous feeding niche. Now, you may not appreciate it, but the nighttime aerial sky is much, much higher density of aerial insects than during the day. During the day, for a small-bodied animal like an insect, is very hazardous. UV damage that they would get from the sun. And in addition, a very small-bodied animal like that would desiccate rapidly out in the sun. So it's hazardous for a small insect to be out in the daytime. And most insects take flight at night. And when they do so, they avoid those hazards. But bats, with their ability to echolocate, can then target those insects that are much more abundant at night. And a bat can go out, and if there's normal amounts of insects about, a good foraging ground, they can eat themselves to their fill, which is a third to half their body weight, in the first hour or so after sunset. It doesn't take them all night long to get the food they need. And so this has been an enormous thing. And once bats develop this, they just radiate it across the planet. And so it's like the geologic history, it's like no bats, and then suddenly there's bats. In a brief blink, once this was figured out, they just radiated everywhere and do that. Now, the disadvantage here is that it's conspicuous. So going around calling all the time, as you're doing for the signals to get the echoes from, it's got to be loud so they can get some range on it. And that means that their potential prey can hear them coming. And a lot of insects have developed a means of being able to detect the bats that are coming toward them. And about half the moths of the world have a simple little modified scale that half dozen neural network system can inhibit the flight muscles. So moths will be flying around, and if a bat gets close enough to trigger that mechanism, they'll just sort of float out of the air, fall out of the air. And that's a really fun kind of action at a distance thing, that if you have a set of keys, you can jingle it and actually generate enough ultrasound from that to trigger that mechanism. So you see a lot of moths flying around a street light or something, shake some keys, and a number of those moths are just going to sort of fall out of the air because you're inhibiting their flight muscles. And mantids can detect this, and katydids, and so on. All right, so there's a predator-prey arms race going on there, and we'll see some bats have specializations to overcome what the insects are doing. So the bats are generating the sound in their larynx, just like I am speaking to you, but shorter, smaller vocal apparatus, so they're able to generate higher frequencies. And there's two ways that they can emit them: out the mouth, like you do, but also there's a number of bats that are what we call nasal emitting, where they're emitting the sounds out their nasal cavity. And that's a little bit more sophisticated way of doing this because it frees up the mouth for chewing or other things when they're still echolocating through the nasal passage. But also these are the bats where you see the elaborate structures on the nose. And so that's for directing the sound, that they can get a more forward beam of the sound that they emit from these nose leaves. And of course, they're taking it further. Related species, vampire bats, have further modified that nose leaf to have an array of sensitive thermal receptors on it. So then they know where is the warmest part of their host to be able to come up and bite and get a good feeding off of them, as you see in this post-feeding toe here and this person's elbow. Okay, that's another story for maybe later. Okay, so bats are difficult to catch, sometimes easier than other times, but this is my party trick I do in field classes. And yeah, here's another little scheme of that. Free tails coming out on emergence, and it's like, let's get one and sample it. And so, yeah, it's not as difficult as it looks, but it's a crowd pleaser. Okay, so bats are putting out these pulses of sounds, listening to the echoes to get a return. And so how do we begin to interpret this? Other animals, such as cetaceans, do this as well. They do it in the water. And we generally, the simple way that we can interpret and view these sounds, we as humans are much more visually oriented. So rather than just listening to them and trying to get something, we typically convert it to a visual display, and then we can tap into our visual cortex, which is more developed on our side. And so we make these diagrams or plots of time horizontally versus the frequency content of a signal. And this is what we call a spectrogram. A spectrogram is a time frequency plot of any wave type of signal. And when it's specific to a sound, a spectrogram of sound, we often refer to it as a sonogram. And so here we see some wave cetacean clicks or pulses, and it's going down. So it's going down and sweeps up. And the scale here is in kilohertz. The unit of a hertz is 1 oscillation per second. So kilohertz are 1,000 oscillations per second. And I've drawn a blue line here at 20 kilohertz, where by convention we define what's above or below human perception of sound. So above the 20 kilohertz sound, we generally refer to that as ultrasound, which is beyond the range of what humans can do. And of course, we know that other animals can hear a much greater range, and they wouldn't otherwise be making these sounds to be able to get echoes from them if they couldn't hear them. And so these whale clicks you can see here are some, there's a part of them that we could hear, and there's a part that goes beyond our range of hearing. So the bats are putting out sound, and the sound they're putting out, because they are the source of the sound, first we have to appreciate that it's limited in the range. And sound from, or any signal from its source, as it radiates outward, then it's spreading out into increasingly larger and larger volumes, which is weakening the signal at any square area that you look at. And this is what we call the classic inverse square rule, is that with each linear distance out, your area that it's spreading out into is the square of that area. And so with each subsequent linear distance, you're losing energy, or the intensity of it goes down by a square of that distance. And so analogy here is a light. So if you have a flash or a headlamp or light source, then things very close to you will be very well illuminated. But as you get further and further away, they're less and less illuminated. You're getting less return from that light as it's spreading out into that greater space. You can still see things at greater distance, but they're not coming from illuminating from your source. Those are what we might consider passively illuminated. And so sound works the same way as it spreads out. But the next thing that we have to appreciate is that when we get to the higher frequencies that bats are using, that as frequencies get higher and higher, they attenuate more quickly with distance from the source. And so lower frequencies travel much, much farther. So you might be able to hear your friend across a field or hear a bird across a field, but if there's a bat there, you're not going to be able to detect it. And it's basically as you go up in higher frequencies, those oscillations in hertz, with each oscillation, you're losing some energy. And so the more times you're oscillating, the quicker that energy is going to be dissipated from the signal. So animals that communicate at great distances, like elephants or whales in not their echolocation, but their social communication, they use very low frequencies and then can communicate at very long distances because it's a lower attenuation rate with distance. But the bats, it's going to attenuate very quickly. And so once bats get more than about 20 meters from you, 30 meters for a very large bat, that's about as far as you're going to be able to hear them. So you're operating in a very limited range of detection. That really plays in then into our detectability when we go out and do surveys. So when we do our surveys, now we're thinking of the other way around the sound coming to us. So if we place a microphone out, then if we look at a unit volume, a sphere around that microphone of 1 unit distance, and say that there's in this volume of airspace, and we assume for the sake of argument here that the bats are equally distributed in the volume of airspace around us, and if in that 1 unit volume we have 1 bat, that bat's very close to our microphone, and we're going to get really good strong signals. We're going to see all the fine subtle details of that signal. And if we go out now just 1 more radius, then we have a shell from unit radius 1 out to unit radius 2. And in that next shell of distance volume, we have now equivalent of 7 volumes equivalent to that inner volume. And so here we're going to start losing some signal detail because of the loss over distance. And if we go out then a subsequent another unit distance, that volume out there from 2 to 3 unit radii is going to have 19 times the volume of what's in that inner sweet spot. And so this is just the physical reality that means when we go out and record, we're going to get a whole lot more low quality signals than the few very good ones where the bats make a close approach to our microphone. And so there's nothing we can do about this. That's the reality of this. And just the comparison of this is, we well understand if you're going out and looking for birds, when the birds are very close to you, you can see all the little details and the primary feathers and the shape and bands on that or whatever. When the bird's a little bit farther away from us, we can start saying, well, it's maybe a flycatcher, but which flycatcher we can't really say unless it was closer. And then when it gets really far from us, yeah, we can say that's a bird, or maybe difference between a songbird and a raptor, but that's about it that you can do. So we have to appreciate this is operating with our sound as well. The distance from the microphone is going to give us varying levels of being able to discern what we have. The difference being is that with our sound recordings, then we can't see distance. We don't have that assessment. When we're doing it with our eyes and binoculars, we can judge it by size and so on. But when we open up and process our recordings, they're always going to be amplified up to a certain level to fill the screen, so to speak. And we have to use other clues that we'll go into as to how we can infer distance or whether we're missing details or not. But here's a typical bat pass going by the microphone. And when the bat's very close to your microphone, we get much more of the full signal detail in there. And when it's farther away from us, we're just getting little snippets or what we call fragments of the full signal. And that's because of that loss of attenuation. And note that along here we're getting, as it gets further and further away, those fragments that are left are mostly just the lower frequencies. And that's from two effects. One effect is that the bats are varying the strength of the signal through their call. So they're starting off a little bit quieter, getting louder through some part of the pulse, and then quieter again. And you can see that reflected on the bottom here, which is the oscillogram view, which is showing us the strength of the signal over time. And on the sonogram, that's mapped to the color in the signal. So the strongest red color here is the strongest part of the signal. But also because these higher frequencies, remember, as you go higher and higher up in frequency, you attenuate more rapidly. So it's generally going to be the higher frequencies that get lost as we get further from, the bat gets further from our microphone. And this comes into play when we start trying to sort out things like, is this a little brown bat or is it a northern long-eared bat? Because we assess northern long-ears, or can tell northern long-ears, because they go up to much higher frequencies than the little brown bats. But we're only going to get those higher frequency content if the bat gets really close to us. If it's farther away, then we're going to lose some of that higher frequency content. So we need to be able to assess them. And one of the clues we use is shown in this sequence here, is that we start to get these harmonic components. And we'll say more about the harmonics, but the harmonics are it's a component of the signal, but it's typically at lower amplitude. So when we get the presence of those harmonics, that is an indication that we're getting some of the lower amplitude content and typically a full signal. So, but when we go out and look at things visually, we know it's at a distance, but when we process it with our sound, it's going to be brought up to, the sonogram is going to be mapped to whatever is the strongest signal down to the weakest signal. And it's an equivalent process of taking an image like this and making it bigger. So we can make it artificially bigger, but we're still missing content there. We're missing information content there. So getting it bigger doesn't make it better. Unless you're like CSI, they have some kind of tool that they can zoom into a photograph from the satellite and like read a license plate. You know, it's like, maybe we need something like that. Okay, yeah, so we get to a point where we can't tell. We can still recognize it's a bird, but we can't say what type. And then we're going to have an awful lot of recordings where we can say that's a bat in there, but we can't say what type it is. So a big part of this practice is being able to know when you can say and when you can't say what type of bats we have. And that's the effect just simply from distance, but there's other effects that are going on here, and it's recording conditions. So yeah, if something is moving and you don't have a proper shutter exposure, you're going to get a blurred image, or if it's through clutter, you're going to get that too. And there's equivalent conditions for this with sound, but with a thing to begin to appreciate again is those higher frequencies that bats are using. As we'll see, they have very short wavelengths, and the short wavelengths are going to be much more affected by vegetation and clutter, but also from atmospheric conditions. When you look at a distance and you see the lights from a town far off, and you see them blinking and twinkling and shimmering, that's from convective heat cells in the air of heat rising. And those convective cells are small on the order of like, half a foot to a foot in size, but those are bigger than the smaller wavelengths of sound that the bats are using. And so little turbulence from airflow and thermal convection, and when the ground's cooling, that will actually affect and give us distorted signals coming in. So we just went over a little bit about the brief intro to the behavior of sound. We're going to go into some more detail on that. But now let's turn a little bit into how the bats are perceiving what's coming in. And I'm going to start off with this, just in terms of perception, is that the perception of humans are this often quoted thing is blind as a bat. And I like to say that's true insofar as you're referring to a piece of sporting equipment, but not for the animal. And this comes from a misunderstanding of appreciating that we use all the sensory input that we have. And although you are, as a human, primarily visually orienting, you certainly use and depend upon your sound and hearing quite a bit as well. And so the notion that just because bats have this ability to perceive things with sound, by no means implies that they're not using visual clues. And in fact, bats see quite well. They see better than we do at night. as with many other nocturnal animals you can think of that don't echolocate. And they are using both of these sensory inputs. And so I like to say it's then fair for bats to go around, talking up us, smack to us as, deaf as a human. That's what they're all chattering about when we see them. But to appreciate how they use both their sensory inputs, then understand that bats are using their echolocation similar to how you use a headlamp or flashlight at night. It gives you good illumination of things up close, but your light is typically not strong enough to be able to illuminate these trees across that meadow or a distant mountain peak away or across a river valley and so on. And think of many of our bats we know, they have a roost, and many of them will commute miles away from their roost to forage out to foraging grounds. And some species like free-tailed bats will go 60 miles away from their roost in a night. And with their echolocation, they're only able to sense things up to about 10 to 15 meters away from them, for the echoes they're getting. So if they're only seeing 10 or 15 meters at a time, they can never find their way back to their roost over great distances. But on the landscape scale, they're using their visual clues. So just as you can see the silhouette of these trees and this pond back here, lake, in the dim lights at night, the bats are actually even seeing that better. So they're getting their landscape scale perception of where they are, how to find their way back to the roost by landmarks on the landscape, but they're using their echolocation for detailed perceptions of things up close to them, such as an insect. So in the dim light, they can't see their insect prey, but they'll be able to detect it using their echolocation, similar to how you'd use your light to, keep from stumbling over a rock or log or something. Yeah.
Do bats also detect the Earth's magnetic field? I don't know if there were any animals that do or not.
There are. That's documented. There are some animals, and in fact, humans have some cells in the front of the brain that have magnetite particles in them. They're like little magnetite crystals in there. And so far as we know, it's vestigial or subliminal in humans' perception. But that's classic studies done on homing pigeons where they put a magnet on the head and confused it. They couldn't home back to where their roost is. There's another classic study, though, done with bats back in the 50s or 60s. It's a barn somewhere in Ohio, big brown bats. And they banded them, and they would take them out of the roost, band them, and they would just take them random 5 miles directions, and they'd be back by the end of the night. And they kept increasing this up to 250 miles. And the majority of them found their way back. Later in the season, it took them weeks from those distances, but they actually found their way back. And at those distances, there has to be some perception that can help them find their way back. So, but active illumination is similar to what the bats are doing with their active echolocation. But so an analogy of how the bats would perceive the world just using echolocation would be like going out with your light on a very foggy night where you're just going to be in sort of this little cloud of perception, and most things beyond that you're not going to be able to pick up at all. Okay, so now into a little bit about the nature and behavior of sound so we understand what that's doing. So sound is, what we perceive as sound is manifested from physical objects moving. It impacts on the air molecules, and those air molecules then bounce on another molecule and bounce on. So it's a domino kind of effect of going out. So you make a disturbance in a medium like this water drop just did, and then that disturbance will propagate out through the medium, one molecule bouncing against another. And the water droplet is a good analogy here, and looking at the surface. Where you see the water rising above the mean surface level of the water means that the pressure underneath is greater. It's pushing up the water to raise it above the mean surface level of the water. But also between those peaks is a trough, and that trough is actually below the mean surface level of the water, which means it's lower pressure than the mean pressure that's in the water. And if you can imagine that this is actually a hemisphere of disturbance pushing out through in the water, that if you link the hemisphere underneath, so if you were down underneath the water, you would feel this pressure going by you. And this one would then meet up with that one. And so it goes down, creates a pressure pulse, and then it bounces back up, and you get this oscillation of positive pressure, negative pressure, positive pressure, negative pressure, and that's propagating out. And so next thing to appreciate then is that this disturbance is able to transmit energy, and that energy ultimately is what's going to push upon your eardrum or the membrane of a microphone, which we can then pick up and interpret these sounds. And cute little example that a wave can actually transmit energy and do useful work is what these two physicists are demonstrating here. Okay, the work is applied at one end and it comes out the other. But that you can do this with sound is shown in this little demonstration where they strike a tuning fork and they're going to transmit sound through this resonating box, and it's going to sympathetically move the other tuning fork, which is then made visible by the bouncing ping pong ball there. So the bat echolocation begins then with vibrating the larynx of the bat. And this vibration happens basically, most all physical materials have a restorative force. So if you bend something, it's going to bend back. And so you push it in one way, and then it's going to oscillate back and forth from restoring force back and bringing you back. It's going to swing past the original position and back again and back again. And so that's undergoing the vocal cords by sending the air through it, and you get the vocal cords to vibrate. And so that's creating this train of positive, negative pressure pulses on the air. And then this will plot that over time of positive pressure, negative pressure, positive pressure, negative pressure. And then that's going to do what we could consider useful work against our microphone membrane to oscillate it back and forth. And a microphone works then by taking those physical movements and converting them into a positive, negative voltage. So then what's going into your amplifier past that point is going to be this electric signal of positive, negative oscillating voltage that is then an electric representation of the frequency content and strength of that signal. And what we do with it will vary from there, but that's the basic nature of what we have. So, how did I get back to? Okay, all right, so now, if we think back to this analogy of creating disturbance, then these little peak pulses are then going to propagate out across the medium. And the speed at which the peak here is moving outward is what we call the propagation velocity in that medium. And if we were to put, say, an oscillator in here instead of just a simple drop, and we oscillate and just move something up and down, up and down, up and down, we're going to get these waves coming out at the frequency or the rate of oscillation of what we're doing. So frequency is going to be how quickly the original source of the disturbance is oscillating. So that would be a slow oscillation. This would be higher oscillation, and so on from there. And so we describe this as frequency. So light also acts as a wave-like pattern. And so we're going from here, in this example here, from shorter frequencies to longer frequencies. And we can see that nature of, if we get far enough away from the disturbance, then we kind of lose the notion that that's a curve, and we can just think of like a flat wavefront coming through here. And we see from that disturbance, we're getting a compression in the leading edge of it and a separation or negative in the back of it. And so, but we think of the air, all the air molecules are already randomly moving due to thermal motion. But if we impart now a disturbance in them, that disturbance is going to propagate outward, and it's going to attenuate, in fact, in part because of that random thermal oscillation going on. And here we're creating just a single disturbance, and we can see that propagating out. But now if we start to oscillate that speaker in the way that like a vocal cord would oscillate, or say the string of a guitar or instrument, then we're going to get repeated oscillations, and we can see those wavefronts propagating out in a more of a continuous fashion. And now if you place a membrane of a microphone here, that is going to oscillate back and forth from that transferred energy, and that's going to create our sound. So, but anything that oscillates, though, will oscillate also at multiple modes of oscillation. So if we have a long string like on a guitar, and if we pluck it, it's going to oscillate back and forth along the full length, but it's also going to be oscillating back and forth on these half lengths, and it's going to oscillate on these third lengths. And these multiple modes of oscillations are what gives sound and musical instruments the richness of sound. And all natural things will oscillate, different shapes will oscillate in different patterns of this. And it's those multiple oscillations that are what generate the harmonics that we saw in that earlier chart. And so vocal cords do this as well. So there will be typically the fundamental, which is the full length of the oscillating material. That will typically be the strongest in energy-wise, and then less energy in that secondary oscillation, which creates the second harmonic, and so on. And so again, that's what gives the richness of sound. You know, we can hear here with Van Halen doing that. If his guitar was just synthesizing pure frequencies, it would not sound as nice as that. So, all right, but now let's get into the behavior of sound and what's happening. And so that distance between the wave crests is what we call the wavelength. So if you got down there and you measured the physical distance between each of these advancing wave crests, that's what we call the wavelength. And this is where we get into understanding really how the sound behaves, because how the sound interacts with objects, a microphone or any other physical object, is entirely dependent upon the wavelength. And so here we see these waves that are made in like a little ripple tank of shallow water. And there's a break here, and these waves aren't no longer able to pass through it. They're getting blocked, but there's an opening here, and then these wavefronts can come through. This is our wavelength, and so this opening is about 3 times the operating wavelength, so the waves can get through. Once you get down to an opening that is less than the wavelength, it becomes effectively an opaque material, and nothing can get through it. And we can see that happening here in this sample. So we can see these wave crests coming down a slope, and there's some detritus in the road there, and the waves are just going around it, and then they're reforming. So just as waves, whether or not a wave pattern can get through an opening, also if you have a smaller obstruction, the waves will either go around it or reflect off of it. And so maybe you can see where I'm taking you on this, but now imagine that these are wavefronts coming out of a bat, an echolocation, or a human. And now if the object is smaller than the operating wavelength, the waves are just going to go around it and reform and keep going. And there's no echo going back. And so this gets us into what the bats are doing. The bats need to get echoes off of small objects. And to get an echo off a small object, you have to have wavelengths that are down the order of the size of the object. And so to interpret that, we can go to our wave equation here, where the velocity of propagation is equal to that wavelength times the frequency. So remember, the wavelength is the distance between these two crests. Frequency is how many times a second you're oscillating this. And so with each unit distance from the wavelength, this tells you how far it's going with each second. And so that gives you the velocity. And so this is what we call a direct proportion. So which is to say that if the wavelength gets bigger, the frequency has to get smaller if the velocity is holding constant. And in fact, that's what happens with sound in the air. It moves at essentially the same velocity for all frequencies. And so as you vary frequency, the wavelengths are going to vary and vice versa. And this matters, come back to here, this matters because of this. So the bats are using such high frequencies. It's like, why? Why do the bats use these high frequencies? because they want to get echoes off of very small targets. And if you have a wavelength that's too big, it's just going to go right around those small targets, and you're not going to get any bounce back or echo return from it. And as I'm speaking to you, the wavelength of my voice is about twice my body length. So I'm never going to be able to echolocate and get or echo from a small bug. I'm going to like starve as a bat in there. But I could put a pillar in front of me and get behind it, or a tree trunk, and you're going to still hear me because those waves are just going to go around that tree, even if you can't see me. You can't see me because the visual wavelengths are tiny, tiny down on the size of molecules. So, all right, you're a bat. You need to get echo off of small targets. And if we go back to our wave equation here, that if you want the wavelength to be small, the frequency has to be big. And so the bats go up to these high frequencies to get small wavelengths. And if we look at some of the frequencies that bats use, and so here's our 20 kilohertz. That's the upper range of human hearing. That's going to give you a wavelength down the order of, about a third of an inch in there. So that would be limiting you to like medium-sized moths or beetles. And you go up to 50 kilohertz, and then you're down to the size of a fly. And you go up to 100 kilohertz, as some of our bats do, you're getting down to like 1.5 millimeters size that you can get an echo off of. Now, it's not just getting an echo off of things, though. Bats actually want to be able to know and get some imaging of that target. And so our bats are so very good at echolocation that they're not just imaging that there's a potential target out there. In many cases, they're actually getting a crude image of the target, and they can assess whether or not they even want it by being able to do that process. And so the higher the frequency you go, it's like having more megapixel resolution in your camera. Lower frequencies, you can perhaps can echo, but not resolve very much. And so that's the trade-off here. Higher frequencies are going to give you greater detail and greater imaging resolution of the target, but they're going to attenuate more quickly. So that's going to limit your range. So lower frequencies, you're going to be able to get more forward range, but you're going to have less detail. And so this right here is going to help us understand a lot of the feeding niches that bats have and how they coordinate or share the foraging and the type of foraging activity you do. Because we have bats that are open air foragers, flying out in open airspace. They don't have to worry about running into branches or other obstacles. They can just blast out these loud sounds and fly quite fast to try to cover more volume of airspace. And that would be like a free-tailed bat or hoary bat. They're using lower frequencies to get longer distance to pick up potential echoes out in the airspace in front of them. These lower frequencies are going to travel farther. But a small bat operating in a cluttered environment where they have to also perceive branches and obstacles and so on, as well as pick up on prey, are going to use higher frequencies. And they're not going to travel as far, but they're not going to be flying as fast. So they don't need to see as far ahead. So one other physical effect to consider is the motion of the object. So if we have a point source and the wavefronts are radiating out from there, but then we move that point source, then in the direction of the approach, that's going to be bunching up those waveforms toward you because it's heading toward you, and trailing away from it, it's going to stretch out those waveforms. And so if you're an observer here, you're going to hear a lower frequency than that which is the actual oscillation of the source. And if you're in the front here, you're going to pick up a higher frequency. This is what we call the Doppler shift. And it's that effect. You hear a train whistle, the train's coming, it's a higher frequency than when the train's coming, or a race car as it goes by. If you're on board either vehicle, it's a constant frequency. It's going to sound the same, but you as the observer is going to hit it. Now, this is part of the effect why no one can ever give you an exact prescription to say this bat is always going to, drop its calls down to 40 kilohertz, or this one at 50 kilohertz or 20 kilohertz, because the bats are moving relative to our microphone. We have no control over that. But at the speed that bats are moving, 10 to 20 meters per second, this only amounts to about a plus or minus 1 or 2 kilohertz. But still, that's part of the reason why all of our, when we say this bat's in this range frequency or whatever, we always have a bit of tolerance in or latitude in those measurements, because we can't control that. So here we have a recorded pass of a bat, and if we take a call sample out from the middle of it, and here's a zoomed view of that individual call, and we're going to put this ruler line right through the middle of the lowest slope part of the call here. And if we take a sample from the beginning of it, then we see it's shifted up a little bit. And if we take a sample from the end, we can see it's shifted down a little bit. And if we had a microphone on board the bat, every call pulse would be just the same. So this is just from the relative movement of the bat approaching the microphone and then receding away from it. So this behavior of the sound, the short wavelengths, is getting into that part that I was saying that we need to be like intellectually understanding, because yes, they need these short wavelengths to be able to get echoes off of small targets like insects. But when we set out a recording, we have to understand that it's not just what the bats are doing with the insects, it's about what we're doing with our microphones and what we're trying to record and how we're going to do it. And if you understand that a small target like an insect can produce an echo, then you can understand that things like vegetation that has leaves and branches and twigs and things that are larger than insects, those are also going to interact with the higher frequencies and shorter wavelengths of the sounds that bats are making. So you can readily place a microphone and hear birds through vegetation, but you're not going to hear bats through vegetation. Any signals that come through you will be distorted by taking multiple echo paths bouncing off of the substrate there. So the only way that you're going to be able to get a good, clear, clean signal of bats is to have open airspace between you and the bat. It's not going to be able to filter its way through the vegetation. And that also applies to bats that are flying overhead. If they have to come through a vegetated canopy, then you're going to get distorted signals as well. And that effect happens from this effect, which you call superposition of waves. So if you have multiple waves now interacting, where they go to positive pressure, and if another one is positive pressure, those two pressures are additive and will produce a larger positive pressure. Likewise, if one is positive and the other is negative pressure, they can cancel out. And in fact, that's the operating principle of noise canceling headsets. If it's a continuous enough steady sound, and then the headphones will generate just the same sound but opposite in phase, and you can cancel the things out. And you can see this effect happening on the shore sometimes, where you've got wave fronts coming in from different directions, and where those two oncoming waves meet, then you'll get the superposition of waves, and then you'll have nothing in between where they're canceling out. And so we call this constructive interference, and we call this deconstructive interference, where you're reducing the energy of the wave. And sometimes that can be very dramatic, like this up the coast near where I live, where this is a Moonstone Beach where people often go out, and low tide you can walk out to those rocks, and people are out there as they normally do, but suddenly randomly from waves that were probably made thousands of miles off the ocean, they all come together in a great bit of randomness and create what are called sneaker waves. And we lose a person or two every year or so that's out tide pooling or something, and one of these random events comes in and then just takes them out. These people, fortunately, all got out, rather wet, but this is what happens. Sometimes you're like jiggling your cup or something, and like one drop flies off, and then you've made this like huge random superposition of waves. So that effect, though, as it manifests in sound, is what causes distortions in our recordings. So if a bat is flying here and you get one direct signal from the bat to the microphone, but another is skipping over a flat surface and producing an echo, this is a longer flight path, and so that signal path is going to be delayed in time, but when they reach the microphone, then these two signal trains are going to interact and create oscillating constructive and deconstructive interference. And because there's just two signals there and they're nearly matched in frequency but not quite, you get this pulsed pattern from the constructive and deconstructive interference. This is what we call the beat frequency, and musicians use this to tune an instrument. That's what a tuning fork is. A tuning fork becomes a reference frequency that you then adjust your instrument to minimize the beat frequency of this interaction, because the closer space they are, the longer is the interval between those beats. So you try to get it down to where they just perfectly match and don't pulse. But we can see that pulsation now if we look at a sonogram of these two signals interacting. So here's the direct signal from the bat. It begins here, it ends here. Here's an echo skipped off a water surface that is smooth and flat. That's what we call a specular echo, which is a mirror-like echo. It's perfectly reproducing the signal. And where they're interacting, we're getting this beat-like frequency. We can see the beats here in this oscillogram view here, and they're manifested in the sonogram as this comb-like pattern in the sonogram. And when you see that, that's an indication that you've got two echoes overlapping. You have a surface close by, and you've got two signals that are directly interacting. And if we just have two signals or just a single echo interacting with a direct signal, it becomes clear what's going on. But more often what happens is if you go out and put a microphone in a position where you're getting multiple surfaces produce echoes, then you have all these multiple waveforms or wave trains that all arrive at the microphone and interact randomly to produce this very chaotic signal. And this is what I call acoustic mush. And it turns out that this is very easy to create, and this is like the typical amateur mistake of going out and placing a microphone for bats. You get a new bat, people get a new bat detector, and they go out, they put the microphone out, and they get all the signals like this, because it's very, very easy to do when you don't appreciate this process. And this process is much more an issue with these shorter wavelengths, because if your microphone is less than a wavelength away from a surface, then this won't happen. But with the shorter wavelengths, it's a much easier thing to produce. And once you understand this, it's very easy to prevent this. And the way you prevent this then is you just place your microphone, you elevate your microphone away from any echo producing surfaces. And if you just go 2 meters away, because sound is moving at about 340 meters per second, which means it travels about 1 meter every 3 milliseconds. And so our longest bat calls, pulses that we deal with are typically something like on the order of about 12 milliseconds. It can get up to about 20 for some bats. But if you're up 2 meters, then that's going to add an extra 4 meters down and back up of round trip distance. And so if you just go up 2 meters, you eliminate most of the echoes. And especially for our shorter, higher frequency bats, they're typically only have calls up to about 5 or 6 milliseconds. And you can get a good, clean, unadulterated, undistorted signal just by eliminating the echoes. And of course, we recommend, though, you actually put your microphone up higher than that. So you go up 4 or 5 meters at least, and that's about the effective sweet spot range. You go back to that slide where we talked about where's the sweet spot that gives you the full signal strength. That's within about 5 meters of the microphone. And so if you're up 5 meters, you're going to be able to get a greater vertical gradient of airspace within your detection volume. And so from an elevated position, you're going to be able to record from there down to the ground and from there up higher, and as well as eliminating these signals. And next, though, is to appreciate that, yeah, don't put your microphone right in the vegetation or try to listen through the vegetation because of this, but you yourself can be an echo-producing surface. And so if you go out with a handheld microphone, you're going to produce this shower of echoes from your body because you're much bigger than the operating wavelengths there. This works fine if you're recording birds because those wavelengths are bigger than you. and are just going to go by you and not create this effect. But the shorter wavelengths that we're dealing with will do this. And so this is why when you see us out doing mobile surveying, walking around, we'll put our microphones on a bit of elevation out of a backpack up above our space, and we can create this sufficient separation to get these really good, clean signals that we can get all the details that we need to be able to make good analysis or get the best analysis that we can. But if you're just holding it in your hand like this, if it's attached right to your screen and you're looking at it, then you're going to get an awful lot of recordings that have this like shower of echoes and mush past it that distorts your signal. So as we'll see, it's difficult enough to tell a lot of these species apart. And when you start losing some of the fine scale details of the signals, it becomes an even worse endeavor. And more so that when you're relying on machine identification, that is best served by giving it the best quality data. So recommendations for recording. Our bats have different ecological feeding niches. Some of them will be up in the open air. Some of them will be out in the open near the ground. We have a lot of species that like to forage along the edges of vegetation. And so if you place your microphone in a position like that, if you go out to the area like where shall I put it, something that can represent and get a little bit of all those different strategy operations the bats are doing works well. So here we have this a pole leaning out from the vegetation here. So it's out far enough to avoid echoes from that vegetation, but you'll get bats that happen by that are operating along the vegetation breaks, some that are just coming by through there, some that might come up from this creek. But we also have an open window to the sky. So if you're along a creek corridor, look up and down it a little bit, see if you can find a place where you've got a break in the canopy above you where you place your microphone, because then any bats that are operating at canopy level overhead, you'll be able to record those as well. Because if you've got that canopy overhead, then anything from those bats will be distorted. So example, microphone placement. And so a lot of times we put our expensive equipment out there. We want to be able to find it when we go back. And so also be thinking stealth mode here. So often when I go out to a location, you'll look around and you can find some deadfall branches here or there. And if you get one of these, attach your microphone to the end of it and then position it so it's reaching out from some existing vegetation, you can pretty much operate your recording in stealth mode here. And in fact, that's where the microphone is in this picture, is on that branch that I just had leaned out from the crook of a tree. And the electronics are put down in the leaf litter where you can't see them. And this was this was down flight from a known roost, and the bats were flying down this corridor to forage at a river farther on down that track. And the other thing to note too when you're doing this is some of our microphone devices have little lights on them, and so also for stealth, think to put some electric tape over the lights, and then they won't be visible at night. The other thing to note here is that this is not just stealth mode from humans, but this is stealth mode from the bats as well. As we'll learn, bats are very curious animals. And if you were to put a pole right here in the middle of the flyway, the bats are going to come down here and say, oh, that was never here before. And they're going to come and check it out and then continue on. But that checking out, it creates what we call inspection phase calls, where they're changing their mode of echolocation to get greater detail on evaluating this object. And as we'll see, those aren't the kind of what we call search phase calls that give us the best species recognition. And so that's a situation in which you're influencing what you're trying to do and not making it as easy. Okay, so here's some example from some field sites. And so the one in the lower left there, there's a reservoir there, and there were wind turbines up the hill behind there. And so we were surveying this as a potential flyway for the bats that might be approaching those turbines. And the only structure there were these buckeye trees. And so we got our pole and we attached the pole from that tree up above, far enough above to get a good sampling of the airspace, but not so close to the vegetation so we could avoid echoes. And here we have a lava tube, and we're trying to sample the bats that are coming back and forth from that tube. And this is a little limited, in fact, because when the bats are first emerging, sometimes you'll get very short call samples that are not quite as good, but often when you're coming back in the morning, you'll get better ones. And so again, along flyways, where you can sort of be at the edge of the flyway, listening out into the flyway, gives you a good sampling without interfering the bat so much. And this is a little bit of Schlieren photography where you use a combination of mirrors and all, and it brings out convection cells and subtle differences in the density of air from the thermal convection. So this is thermal convection just from a human, and you can imagine like a hot rock or ground in the evening when we go out to record. But you can see the scale of these convection cells, and that they're down on the order of size of the wavelengths that the bats are using. And so we actually go out and record at one of the worst times of night when we've had a warm day, the air is cooling, the ground is still warm, and you're getting convection cells rising up off the ground. And so be mindful of that as well. If you go out to a pond or location to record, and you've got all this nice vegetative ground over here, and you got these nice big rocks, and you might like them because they feel good and warm to you, but if you place a microphone over there, you're going to have all these convective air cells moving up and down, and that's going to distort your waveform, your wave trains as they're going through that. Okay, so getting into a little bit about the bats are interpreting what they're doing. So the bats are putting out these sounds, and to get the most out of them, just as you can see better with a brighter flashlight, the louder the sounds they make, the more perception that they can get for their echo. So a lot of our bats are vocalizing very loud. Big brown bat, typical around 110 decibels when it's out in the open. And remember, the threshold of pain in hearing for human is 90 decibels, and decibel is a logarithmic scale. So it's not just 10% greater sound. This is 100%. No, 10 times the sound energy to go from 90 to 110, no, to 100 decibels. This is 100 times the sound energy to go that far. And so what that means then, on the order of that change of sound, is that it's very loud. And if you subjected your ears to sounds that loud, then that's going to render your ears less sensitive for a while to be able to hear. And so bats have this real challenge, biological challenge, of generating these very loud sounds right next to their ears, and then milliseconds later having to hear very quiet sounds, because just an insect target that's 1.5 meters away from the bat will have a 45 decibel less power in the returning echo. And so that is a tremendous difference in sound. So it's this very loud sound, and moments later they have to hear very quiet return signals. And so first, of course, the bats can't hear when they're vocalizing that because they're going to overwhelm any sound. But also they can't hear when they're vocalizing because they have a mechanism going on in their ears that's actually turning off or attenuating the sound perception that they have. And so and that's accomplished by those little inner ear bones, the malleus, incus, and stapes. Well, the last one before the inner ear is the stapes bone, and that's got a little muscle on it, the stapedius muscle. And when they're vocalizing, that muscle contracts and attenuates the transmission of sound into the inner ear. And so that protects their hearing, and then just as soon as they're done vocalizing, that releases. You've got that too, but not as well done as the bats do it. So a typical bat is echolocating about a 5 millisecond long call and about 12 calls per second. And so during that 5 milliseconds, when they're vocalizing, they can't hear any echo returns. And so that means they're going to be essentially blind to things very close to them because they can't hear an echo return during that time they're vocalizing. And then, 70, 80 milliseconds later, they put out another echolocation pulse, and they can't hear that one. Then they can't hear any echo returns either through that. So that'll make them then not be able to pick up targets at about 20, 25 meters away, depending upon their repetition rate. So they're going to have these gaps in their perception. when they're doing this. And this is something that's, on occasion, a bat might be flying along, putting out search phase calls at regular intervals like this, and then suddenly, boom, something like springs up in front of them because it had previously been missed in there. So this is just something that they have to deal with, and their brain does the perception to get it working. So here's our smallest North American bat. This is the Western version, similar to the tricolor bat that we have out here. And so here is a train of echolocation pulses from that bat. And so when they're just out flying along, making regular pulses, this is what we call the search phase. And this is the bat flying along, searching for prey or to obstacles that it needs to avoid. And this is the bat in a regular flight mode. And in fact, these search phase call pulses are synchronized with the wing beats, because to generate that much sound energy, that requires energy. And so they get some synergy out of synchronizing the wing beats. So when they're pulling their wings down, they're getting compression of their chest, and they're helping to use that to expel the air through their larynx. And so we'll see then that the search phase calls right away. You can interpret that smaller bats are going to have a higher repetition rate in the search phase than larger bats because of different wing beat frequencies. That's going to play into them. And we'll also see sometimes in our recordings that it'll be missing a pulse, but you can fill in that that's like a double interval from the previous ones. So they do synchronize their pulses, their echolocation pulses with their wing beats, but not every wing beat do they always give you an echolocation pulse. Now, the bat flying along, and here it gets an echo return. So it gets an echo return here, and at this point, then it's got an echo, and now it's going to investigate where that echo came from. And so this is what we call the approach phase. So it's flying along, boom, 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 and then it detects an echo over here, and then it's going to start turning and tracking and coming toward that potential target. And the repetition rate is increased here. And with many of our species, we'll see not just the repetition rate is increased here, but the frequency range or sweep of the calls are going through. So when I described those open air bats, like a hoary bat or free-tailed bat that has these lower frequency calls, they won't have as much sweep through frequencies. But when they switch into the approach phase, they will have more sweep through the frequencies, because that gives them more precise timing information to where the signal is, and more imaging information by applying higher frequencies in it. And so during this approach phase, this is where they're tracking the target, but also evaluating it. They're getting close enough and having high enough sweep through frequencies that they can begin to image the target and to come to an understanding if they even want to get that target. And as it turns out, bats have a lot of feeding preferences, and not just from species to species, but within an individual species. We did a study 5 or 6 years ago in Yosemite with colleagues where we did stable isotope analysis and found that even within like 50, 60 samples from one species, that they were all feeding at different trophic levels and maintaining them when you compare the short-term and the long-term samples, like hair to blood in them, and which indicates that they have different feeding preferences within the individual species, and they're sticking to them. So some decide they like spiders, some decide they like this prey item or whatever, but they actually get them. And cool thing from that, because that means that they both have sufficient food availability that they can be selective, but also that they are selective. So cool thing. So what we'll see sometimes is that we'll see bats go into this approach phase, but then not go into this final phase, which we call the terminal phase, which is at this point then they've tracked the object, they're nearly upon it, and then this is the last little bit of real staccato, quick repetition of calls that they use to precisely position and capture the potential prey item. And you'll see search phase, approach phase, and then not go into the terminal phase occasionally, because that means they've decided that's not a target they want to have, and they will go on to the next. And so what's happening, what they're doing here is sort of like, imagine that you've got a flashlight, but instead of a continuous beam, you just push a button and you get a little flash. And if you're just walking along, you're fine. Flash, get an image, walk into it, flash, get another image. But if I throw you a Frisbee, then you're going to be going flash, 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 or a baseball, flash, 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 to try to catch it so that you can track it. And so they're using their calls similarly. This last little terminal phase does not have the frequency sweep to give them lots of position or imaging information. At this point, though, it's just about target acquisition. So the fast repetition rate here will give them the time between the echo to the turn to precisely position the image so that they can, or prey item so they can capture it. So when we're listening to it in a real-time detector, that sounds like a buzz because it's happening so quickly. So we call that the feeding buzz. And if we listen to it, you can hear the search phase, approach phase, terminal phase. And yeah, we'll go again, search phase. Now, we can hear those frequencies because this is slowed down by a factor of 10. So what's a 40 kilohertz signal is coming out of this as a 4 kilohertz signal, and we can hear it. But that also means that this entire sequence of events that just happened 10 times as fast. So this scale on here is in milliseconds. So that entire sequence of events happened in 1/3 of a second in there. So this is high speed operation here, high speed analysis. And if we listen to it in like a bat detector would give it to us, it sounds like this, real time. And you can hear the buzz at the end. Yeah, so that's all happening that quickly. And here we got some high-speed videography, and we can see how the bats do this and catch. That's the terminal phase, slowed down a lot more. And the bats are using their wings like a mitt. So they catch it, sweep it in the wing, toss it down into the membrane between your legs, and that's where they actually take it into the mouth. And we're going to see a couple of bats here miss because these are tiger moths, which not just can hear the bats coming, but they actually generate sound through stertulation and can actually jam their ability to hear this terminal phase at the end. And you see that moth survived the attack. And fun fact, about 95% of bats are right-winged and about 5% are lefties. They prefer using their right wing. And getting jammed out here, you can see some of these switching and using the left wing. So I kind of didn't quite get that one. I think, no, that moth's not going to make it. Okay. All right, so here's another variation on this. Is a red bat. And so red bats, they have a longer, larger interfemoral membrane, or the membrane between their hind legs, and they actually just like go directly to that, and we'll catch the prey item in that. And this next little clip here is from one of my former grad students who does, you might know Aaron Corcoran.
Oh, yeah, so these look like Aaron's video.
This is Aaron's video, yeah. Yeah, this is a Townsend long-eared bat, like your cornurinus out here. And this is and Aaron works on, like Dave does there, flight dynamics. And Aaron's looking at like how quickly can the bats turn in response to the prey. And so this is a moth that is responding to the bat. And you can see when it plays again, when the bat gets up close to it here, that the moth just like falls out of the air. And that's triggered that response from the moth right here. You see the moth just like descends down. And that's because it heard the bat call, pulses coming at it, and it tried to do that. But here you see the bat recovers and it's not going to get away with it. But these cornurinus are moth specialists, and so they're very maneuverable, and so can outmaneuver a lot of the moths that are doing this effect. Okay, so getting into a little bit now what we're going to do, which is being able to take this knowledge and be able to look at these signals we're getting from the bats and then be able to try to tell one bat from another. And our first thing to recognize is that bats are not birds. Yeah, you all know that. But but appreciate that the sounds that birds are making are entirely different function and selective pressure than the sounds that bats are making. So we have this great history of birding by ear. And when we first started making bat detectors, everyone was like excited. It's like, now we can go out and bat by these sounds like we've been doing with birds. And no, it doesn't work that well. It doesn't work as easily. And it's because birds, their calls are selected from species to species to be different. They're selected to be identifiers, to say, this is who I am, this is where I am. And as such, there's no constraint on complexity. They can be multiple syllables and notes and trains of them together. But the bats are using their sounds that we're recording for the utility function of putting out a pulse, getting an echo back from which they can garner information from it. And as such, they're selected to optimize that task of getting information back from these signals. And as such, different species that have very similar information gathering tasks converge on having the very similar signals because that's the best solution to that task. There's no selective pressure for one species to make different echolocation calls than another species. So yes, we can do this and tell most of the species apart rather well because they're doing slightly different information gathering tasks, going after slightly different prey in slightly different ways. And so that gives us enough differences in their own echolocation pulses. But we've got a lot of species that are doing similar things and do have a lot of overlapping call characteristics. And so we're left with then having to work with the nuances to tell some of them apart. And that's why it's so important to get those good, clean recordings to ferret out some of those nuanced details of the signals. So in general, when we're describing these signals, the calls range from being what we call very low bandwidth, as the one on the left there, that is not sweeping through very many frequencies. That's a call that comes from a hoary bat operating in open air. And so it's at lower frequencies, so that sound can travel farther, has greater range to be able to detect an echo. But by having it not sweeping through very many frequencies, you're essentially getting this longer duration signal, and that will give it a longer duration echo. And that gives it the ability to detect targets, again, that are farther away. Because think of, if you're not quite sure if you hear a sound, you'll pause and you'll listen for a moment, and you're letting, it's a process of neural integration of the signals coming in. And so if it's just a really quick signal and it's very quiet, you're not sure if you heard it or not. But by having a longer duration signal, that enables the bat to be able to detect targets farther off. So it's accomplishing that by both having a lower frequency sweep, longer duration call at a lower frequency. Now, that bat, once it goes into its approach phase though, if it detects a signal and starts to track it, will convert to having more sweep through frequencies. And sweeping through frequencies, we call that a FM, or frequency modulated signal. And so this is going to give much more precise positioning information, because remember, the bat will interpret its the distance to the target by the time from when it does the call, the time when it gets its echo back. And if it's a longer duration signal, then that's going to be smearing the distance to the object. It can tell it's out there, but once it wants to start getting more precise positional information, it will switch to a frequency modulated signal so that it's going to be able to have multiple frequencies from which it can assess the timing to this part of the call, the timing to this part of the call, the timing to this part of the call, timing to this part of the call, as well as getting more detailed information on the shape of the signal. So frequency modulated signal is going to give it more precise target distance, as well as more imaging information along with that. Now, there are many of our bats, this is from a fringe myotis, which is similar foraging strategy to like the northern myotis out here, sweeping through a lot of frequencies. They will use that as their search phase call. So some of the bats that are operating in clutter, closer quarters, will just always use frequency modulated calls for search phase as well as approach phase. But many for open air bats will switch between lower bandwidth calls to higher bandwidth calls when they go into their approach phase. So to kind of take a sample of a lot of different species, here's a sampling of some of our western species going from the pipistrelle, which we now call the canyon bat, AKA out here tricolor bat, to a myota, a couple of myota species, down to a pallid bat, that's like a big brown bat range of call, to a free-tailed bat, and a cornurinus, and then a spotted bat, which is one of our Audible species that we have out west. So this is showing you sort of the range of frequencies and timing differential that the bats or calls are doing. And when we zoom out like this, there's not all that much difference from signal to signal. They're all going to be simple, discrete pulses, and that accomplishes the task of echolocation. Because if you repeat frequency, if you sweep up into a frequency and back down again, then it's going to confuse the signal because you'll have a frequency from here and a same frequency from here, and that's going to mess up your timing. So the best tool for getting information back are going to be simple single sweep pulses, and most of our calls are like that, and we'll see sometimes other features on them, but they have used in other contexts, perhaps adding some social information to the call. Now, those are all those 8 bat calls that we have on there, and down at the bottom in red is below the human limit of hearing, and that's me saying bat. So in addition to, as I said, about how quickly this process is happening, in the time it takes me to say bat, all those bats could have made multiple pulses in there. So it's entirely different frequency range than we can account, but it's also a different temporal scale than we're aware of. But now we can start to appreciate from some of these different call shapes and types some of the ecological context in them. So we go from open air foraging bats up above the canopy or out in open airspace. They're going to have lower bandwidth calls, typically at the lower frequencies. Their wing shapes will also match what they're doing. So these are going to be bats that have what we call high wing loading, which means that it's more loaded for each unit surface area of the wing. That means smaller wing area per their body mass on there. That's going to reduce drag, let them fly faster. So these are more like a swallow or a swift wing versus something that's more like a harrier wing, which is broader and lower wing loading. And that will give them more maneuverability. So this is a fast flying, not as maneuverable bat. This is a slower flying, more maneuverable bat. And this will be a bat operating in more cluttered space, having to avoid obstacles as well as detect prey. And then we've got our edge habitat foragers that are kind of operating half between open air space and vegetation. So one's operating in clutter, and we'll get these differences. That said, we talk about species that are doing these things. Well, some species are generalists, and all within a species, they can adapt a little bit more. So even within a species, we'll see that when it's out in the open, it will reduce its bandwidth. And when they're in cluttered space, they'll increase the bandwidth. So there's a lot of plasticity within an individual species as well as these general species differences. And then in some parts of the world, we have bats that make a high frequency, constant frequency call. And not so much here in North America, but in other parts of the world, that's a pretty sophisticated call type. And what they're doing is these bats are operating often in a cluttered environment and putting out this constant frequency call. And it's a way of filtering out obstacles around them versus the insect prey. Because the insect prey, everything from a fixed object will return a constant frequency echo. But the insects, with their wings going back and forth, when the wings are pulling away from the bat, that's going to lower the frequency from the Doppler shift, and wings going forward toward the bat, that's going to increase the frequency. So the bat could put out a constant frequency call, but echoes it gets back from a prey target with wings will be warbling. It'll be a little, it'll put out a call that says, but it'll come back with a warble in it. And so essentially filtering out fixed objects from prey objects, which is a pretty sophisticated way of going about it. And here we go. So what we see here is a compilation of calls from one species, red bats, sampled from different bats operating in different flight conditions here. And so this is, again, this is not a temporal sequence from one single bat. These are just samples from that species in different places. And so within any one species, when it's operating in a cluttered environment, it's going to use shorter calls, more calls per second, versus breaking out in the open airspace. It's going to be flying faster, lower bandwidth calls, fewer per second. And so our task in recognizing our species will be to recognize this entire call repertoire which each species has. So within any given species, it's going to have different call types and shapes. And so this is the great complication. Yeah, a lot of our bird calls will always be the same. That bird's always going to make the same call, or a song with similar syllables. It might mix it up a little bit, but it's going to be much more consistent. Our bats, on the other hand, are not just making one type of call all the time. They're going to adjust the calls to some extent given the task at hand. And our task out of this is to then recognize that every one of these different calls here came from a red bat, even though one versus the other looks quite different. And so what we'll find, and this gets into when we now get into doing the vetting of being able to say, is it this species or that species, recognizing that all of our species have a repertoire of call types, and within that repertoire, some parts of the repertoire of this species will overlap with some parts of the repertoire of that species, and to recognize what are the ambiguous call types versus the call types that are more specific or discriminating or unique for that in that species. Those discriminating call types are the ones that we want to focus on to say confidently this species is there or that species is there, because the overlapping ones are going to be more problematic for us. And so how do we calibrate this whole system? Well, it's quite easy to record bats. You put a microphone out, bat's going to come by, and you're going to record it, because again, they're making quite loud sounds. And if people could actually hear bats, they would have been persecuted over history even greater, because in many places the night sky is so full of sound that humans wouldn't be able to sleep. So maybe they take to sleeping in the daytime when it's quieter. Who knows? But that doesn't work with visual, does it? But the difficult part of recording bats is knowing who says it, because again, they're up in the dark. You hear a bird call, you've got two different ears that can help you get a directional sense on where it's calling from. Then you can see the bird making the call, and it's very easy to put sound with animal. It's very difficult to put the sound with the bat, because they're up in the dark. We can't position the sounds unless we use more sophisticated listening devices. And so it's taking us a long time to be able to get enough recordings that we can precisely describe back and know what species made it. And so some of the ways of doing this would be a little device like this, where we put this elastic tiny little mini bungee, elastic sewing thread onto a bat, and you release it on one end of a fixed monofilament line, and it gets into a little bit more steady mode of flight, and then you record it as it's going by. And that's one attempt, and you can get multiple attempts out of this, because if you just release it by hand, it's going to fly off in what direction you don't know and not get it. But as we'll see, these initial flight calls are not representative of what it does when they're flying out under normal mode of flight. But this gets us on that short end of the repertoire. Other way to do it is to be able to recognize bats as they're flying on the air. And our colleague here in the red, Chris Corbin, is the master at this. He can hit it with a high power spotlight, and he can, for a lot of species, recognize one species to the other. So if you're with him and you can catch some call samples before it gets zapped by that bright light and gets stunned, but you know what bat you just recorded. But over time, we found the best way of doing this is to put a light tag on a bat, and then you can visually track it. So that adds the visual recognition of the bat. And then when you're recording something, you know who's saying it. But you have to be careful, though, that even if you're recording something, that it's the one with a light tag and not some other bat that you can't see in the dark, just closer to your microphone. So this is a manual process in which you have to watch the movement of the bat, and see, if you see it's approaching you see that or listening that you're getting a stronger signal, and then it goes away, it's getting weaker, so that you can confirm that what you're observing is what you, in fact, you're recording. And we have done this and built up our reference material over many years, and this is a slow process because very often they'll just take off and leave the area. But when we do this, we'll have, like in a big open area, a number of people with recording units. Hopefully the bat will go by one of them and be able to pick up a recording if all goes well. So we have to catch the bat. And then these are some older light tags we use. Long back, we used to use just little mini Siloom sticks. Then we went to these little LEDs, and we have another version of LED we've been using since these. But we just basically take a little bit of goopy school glue for a temporary attachment, put it on the underside of the bat so that you can see it from when the bat's above you, and that when the bat gets back to its roost, it can readily take it off. And we've seen them do that a number of times to get up onto a tree or a ledge or something, and then you see the light tag fall off. So we equip the bat, and then it's ready to go, and we release it. And this gives us the ability to be able to get these longer duration calls, because zip line or hand release or just at a roost where the bat's first initiating flight, you're only getting these shorter duration calls. And when the bat settles into its flight and is doing its search phase calls, it's doing these longer duration calls. And so these are the kind of calls that we need to get reference recordings from and know it's that bat making these calls, because when we place our equipment out for passive recording, these are the kind of calls that you're recording out when the bat's actually doing its thing. And these shorter calls happen just on initiation of flight, or if the bat's in a very cluttered environment. And so for our Myotis species, those are typically calls that are like 4.5 milliseconds or shorter. But when you're out actually foraging and doing their activity, they're longer duration calls. So it's really easy to get reference recordings of these shorter ones, but they're not actually going to serve you to be able to recognize the bats when they're out doing this activity. And that's the difficult part. And in fact, if we look at how well you can classify the different species with shorter calls versus longer calls, the shorter calls between these two species are nearly identical because they're doing the same task. They're initiating flight, they're orienting, they're figuring out where they are. They're not searching for insects and prey items. And so these bats both have slightly different approaches to foraging, and so they have slightly different calls when we get to longer type. And so it's those longer types that we need to be able to put this together. And so at about 4.5 milliseconds there is where we start getting more species discriminating call types. And so if we look at a cluster here of the call duration versus what we call the characteristic frequency, when the calls sweep down where they achieve the lowest slope toward the end, that's what we call the characteristic frequency. And so it's these longer call varieties that you get when the bats are out actually foraging. And if you just record something leaving a roost, you're getting those shorter duration calls that are less discriminating for species. So it's often something we want to do is there's bats leaving this roost, we've got bats in this roost, what kind of bats are there? And if you just record them as they're coming out, you're going to be challenged to get a confident assessment of the species. But if you can track them and watch where they're going and get as farther and farther, the farther that you can get from a roost and still record them knowing those are the ones that came from that roost, you're going to get better and better samples that can give you better species recognition. So this is the process where we got a lot of the reference recording. So we release the bat, and right in this close region where the bat's first taking off, you get just shorter calls. In this case, the bat left the scene here on this long-term exposure, and then it actually comes back into view here where it's going along the edge of the vegetation here. There was someone out here recording. That was their light from their recording unit. They got a little bit better sample, but it kept going, and there was someone recording way out here, and they got a really good recording sample from there. And you can see some other examples of this. This is some of the things we've done over the year. John made these pictures, some very like stunning pictures. You can see the person releasing the bat here, and it misses the ground, flies up, goes to the tree, back up again, and then it's settling into a flight here, and hopefully this person got a good recording from that bat as it came back over. And so we would take these recording with modern equipment. We can turn these over much more quickly, and then be able to do the analysis on them and put them into our classification systems. And yeah, so this one shows it a little bit nicer. You just first release the bat, and if you're right close to where it's releasing, that's where the bat is just making these short calls. It's going around, making these quick turns, figuring out where it is, orienting, and then it takes off here. It breaks into the trees there and breaks out. That person on the left there gets a little bit better sample, but there's another person farther on down that road that got the really good recording sample on that release. So bat begins transitioning, and then best ones a ways on down there. And so just a few of these, I'll say, scrumptious pictures. This action. And this is actually, I think that, yeah, Indiana bat here. And we put the tricolored tag on the tricolored bat. So when we're doing these releases, we'll put different color tags on different species, because the best samples you get are if that bat hangs around for a while or maybe comes back a little later in the evening, because then it's absolutely going about its normal business. And if we got different colors on different species, then we can still know that one's an Indiana bat, that one's a little brown bat, that one's a tricolored. Okay, so that's bringing us to, I think, to a good break.
Okay.